In this video, we continue our look at using substitutions to help us solve first-order differential equations. So previously, we looked at a type where, we identified a certain inner function, and based on that, we made that our u, and we were able to convert it. Well, the process is going to be somewhat similar with a couple, key differences as we look at solving what's called homogeneous first order differential equations. Now, the word homogeneous, it tends to show up a lot in the study of, well, equations in general, but definitely differential equations. And you have to be careful because the same word is used in several different contexts, right? So this is the context of first order differential equations. So let's write down what the definition of a first order homogeneous differential equation is, and then talk about how we solve it, and then just do a couple examples, right? So a homogeneous first order differential equation is one that can be written in the form, right? So this one again is based on the normal form, and it's of the form where you have a function on this side, but now it's a function of either x over y or y over x, right? And that looks a little strange, but basically what this is saying is anytime you have a variable on the right hand side of your normal form, then it has to be a ratio of two variables. So I can't just have an x by itself or a y by itself, but I would have to have like x over y or y over x. And whenever that's possible, we say that the differential equation is homogeneous. So before we talk about solving these, let's just look at a couple examples of differential equations that can be classified as homogeneous or not, right? So let's just look at a couple examples. So we won't solve these. We'll just see if we can get them in this particular form and take a look at some of the algebra that might be needed in order to write the differential equation in a particular form. So let's look at this first one. Let's say we have x times y times dy dx, and then plus 4x squared plus y squared is equal to 0, right? Just a little look, we can see right away that this differential equation isn't linear, right? And what makes it not linear, there are two things. The more obvious one is the fact that our dependent variable y is being squared. But a less obvious one is that, look, we have a function of, we have y multiplying dy dx. That can't happen. At most, what we can have is only an x function multiplying dy dx. So there are two reasons here why this differential equation is not linear. So this one, right, we can't have a y multiplying dy dx. So that makes it nonlinear, as well as this, right? So as much as we might like integrating factors, it just wouldn't apply to this differential equation. Now let's see if we could maybe make this separable. Now in order to see if it's separable, we have to put it in the normal form, right? So let's go ahead and solve for dy dx, right? Let's put this in normal form and see what happens, right? So first, let's subtract the 4x squared and the y squared. Let's move those terms over. So we would have xy times dy dx, and then I'll have negative 4x squared minus y squared, and then I'd have to divide everything by xy, right? So I'd have dy dx is equal to, and then I would have negative 4x squared minus y squared all over xy, right? And the thing is, because of this difference here, because of this subtraction, there's no nice way for me to factor the top so that I can get a function of x times a function of y. It works in the bottom, right? Right, because I can see the product x times y, but there's no way for me to factor this so that I have a function of x times a function of y. So this tells me, again, another red flag, this is not separable. Right, so we couldn't use separation of variables on this. However, if we look closely and kind of rethink this fraction, right? Instead of having it as a single fraction, what if I were to write this as two separate fractions with that common denominator? In other words, what if I did this, right? So here's our little algebra trick of the day. So if I took the negative 4x squared and put it over xy, and then did the same thing with the minus y squared, put that over xy, then I could reduce this fraction, and I could also reduce this fraction. So look at what dy dx is. So dy dx is equal to, so I'll put the negative in front. I'll still have a 4 and an x in the numerator, but then the denominator, I would lose that factor of x. So I end up getting minus 4. In fact, let me write it like this, x times y, right? And look at that, there's that x over y form. And then something similar happens with the second term. Now, the y's can be reduced, right? Because I have two factors of y in the numerator and one factor of y in the denominator, so I can write that fraction as y over x. And there you go, right? This now tells me that this differential equation is homogeneous, right? The fact that when I used my algebra and I did it carefully, everything on the right-hand side that has a variable is either expressed as a ratio of x over y or y over x, right? So as you can see, I wouldn't say it's anything non-standard that we've done, but you know, until you see it, you probably wouldn't think of doing something like this. But this is exactly what we would need to do to first identify the differential equation as being homogeneous, and then in a little bit we'll talk about what do we do from here? What's the next step, right? But again, before we do that, let's do another example of trying to see if a differential equation is homogeneous or not, right? So let's take a look at this one. Let's say we have, so call this number 2. Again, let's say we have x times dy dx. And then on this side we have y times the quantity, the natural log of x, minus the natural log of y, right? And again, what we would like to see is when we put it in that normal form, every time we see a variable, it has to be a ratio of two variables. I can't have just an x by itself or a y by itself. It has to be a x over y, y over x. Well, actually, you know, when I look at this one, the steps to get it in this particular form, it's actually maybe somewhat easier, you might say, because remember we have a property of logs that says if you're taking the difference of two logs, it's the same as taking the log of a ratio, a quotient, right? So I can combine these two logarithms into one. So I'll do that first. So then I have y, and then what I have is times the natural log, and then here, there I go. I have the x over y. And then you see, I do have a y by itself on this side, but then if I divide both sides by x, right, since this is a single product here, then I get it in the required form. So if I divide both sides by x, I'll have, now you might say, well, I'll have to write it like this, and that's fine. But again, there's this a nice property of fractions that if I have AB over C, you can write that as A over BC, or AC over B, right? As long as I have the just that single term in the denominator, I can sort of rearrange in other words, I can group the products or the factors in different ways. So yes, I can write this as y over x times the natural log of x over y. And there it is, right? I've expressed the right-hand side of my differential equation in such a way that all the variables are a part of a ratio, right? And that it's not just any ratio, but a ratio where the exponents are the same. All right, so we can say that this one is homogeneous, right? So now that we have at least a couple examples of what they look like, how do we solve them, right? Well, it turns out that we follow a very similar procedure to our first substitution method, where we used u. So I'll go ahead and we're going to use a u sub again. But it will be a little bit different because what we're transforming isn't an integral, we're transforming a differential equation, right? So if dy dx can be written in one of these forms. Now I'm just going to write it in terms of y over x, right? And they don't always have to show up as, y over x and x over y. It could be one or the other, right? So let's just say we have it in this form. The substitution that will always work is this, right? So the substitution u equals, you guess it, y over x, right? So if you just take that inner function, the y over x, and make that your u, this substitution always converts the homogeneous differential equation into a separable one, right? So always converts the homogeneous DE into a separable one, right? And remember, separable in many respects is the easiest type to work with, right? It's easy, contingent on those integrals that we have to evaluate, right? Anything that involves integrals, we have to be cautious when we talk about ease. But as a process, it's fairly easy to describe it, right? All right. So so let me kind of just write down something a little bit in general, right? So if we have dy dx is this, and if I let u equals y over x, well, that takes care of this part, right? That takes care of this part. So I would have big F, and then in parentheses I would have u. Okay, that's fine. But I can't leave it like that, because that means I would have a single differential equation with three variables. I would still have a dy, a y here, I would still have an x there, and then I'd have a u here. It's not allowed that we have a single ordinary differential equation in terms of three variables. So what I would have to do, just like I did with the previous substitution method, I would have to find a way of replacing this dy dx, right, with something that has du dx. right? Well, we have an equation here that involves u and y and x. So surely there has to be something we could do with this equation to get dy dx out of it, right? And the easiest way to say it is to do it like this. Now, we have a fraction on this side. We could go ahead and use like the quotient rule, and differentiate this. But, the quotient rule, I would say, is probably the most involved of all the rules of differentiation. And when possible, I try to avoid it. Not that it's bad, but hey, if I can find a slightly easier rule to work with, then let's go with that. So what I'm going to do is I'm going to solve my equation here for y. So let's isolate y. So y is equal to u times x. So I've turned this equation that has a quotient into one that has a product. And then what I'm going to do is differentiate this equation with respect to x. And I will get dy dx, right, on this side. But then on this side, I'll have to use my product rule. So let's differentiate with respect to x. So our product rule says take the derivative of the first. So that will be du dx times the second. And then plus the first, which is u, times the derivative of the second. Well, the derivative of x with respect to x is 1. So there you go. So in other words, let me write this one more time. So dy dx is equal to du dx times x plus u. So that means if I use these two equations, this one to replace the y over x, and then this one to replace dy over dx, then I would have converted my differential equation from one that has y as the dependent variable to one that has u as the dependent variable. And the thing is this now separable? Now, I could do it symbolically, and yes, I could show you that it separates, but I think the time will be better spent if we actually do it on an actual differential equation. So actually solve one of these things and then see what the process looks like, right? So basically, what I have highlighted here in blue are two standard formulas that will always apply as long as the differential equation is homogeneous, right? So it's like a contingency. If it's homogeneous, then these two equations can be used to convert the differential equation into one that's separable. If the differential equation is not homogeneous, then we have to throw this method out and find another one, right? And that's how it goes with differential equations, all right? So let's take a look at this example, right? So we'll see. Maybe we'll get a couple examples in. So let's say I have 2xy and then times dy dx is equal to 4x squared plus 3y squared. All right. Well, let's do that trick that we did previously. Let's go ahead and divide both sides by the 2xy. But what I'm going to do now is actually write it immediately as two separate fractions. So dy dx is 4x squared over 2xy plus 3y squared also over 2xy. And the same thing happens. Now I happen to have a few different constants here, but let's see what happens. So the first fraction reduces to 2 times x over y. And the second fraction reduces to 3 halves y over x. All right, so good. So we see that it's homogeneous. Now we're going to make the substitutions that I have highlighted in blue, and these are like canned. They don't change, right? Because this form is just so specific that you always use it of this form, and then this derivative always follows. So if we let u be equal to y over x, and sometimes this equation is helpful, the y equals u times x, so I'll go ahead and write that down. Right? So this follows directly from this, and then by differentiating this, we get the third equation. But this is the key, because this is the equation that gives us the relationship between dy dx and du dx. All right, so let's plug stuff in. Now, as far as what we're going to do on this side, there are a couple ways we can handle it. But if u is equal to y over x, then the reciprocal of u is x over y. So this is how I can handle both of these forms. All right. So where's everything going to go? This is going to become this. Well, let me write like this. So the y over x, this one will become this, and then the x over y will become 1 over u, right? So the things, they're color coded now, so the stuff that's coded down here will replace the things with the corresponding color up here, right? So let's start and just write everything in terms of u, right? U and x. So I have du dx times x plus u, so that's this side. And then 2 times, instead of writing x over y, I'm just going to write 1 over u. And then finally, instead of writing the y over x, I'll write 1 over u. So I have 3 halves times 1 over u. All right. Okay, so in order for this to be separable, right, I need to collect all the terms that have a u, right? So I need to get this on that side. So before I start multiplying by dx, I'm going to collect all the u's together, right? And in fact, I think I just realized an error. The the y over x is just u. It's not 1 over u. There we go, that's u. All right, so what I'm going to do is subtract u from both sides and then just sort of clean this up and maybe go ahead and write this as a single fraction now. Now that I've sort of, put it in that homogeneous form, I've made the substitution. Now let's start to simplify, because what's upcoming is an integral or two, right? So we got to make sure that things are in the nicest possible form that we can integrate. So this, I will write it as 2 over u, and this is 3 halves u, but then I subtract u, so minus 1 u. So 3 halves u minus 1 u is 1 half u, right? So I have 2 over u minus u over 2. Not too bad, but again, if I'm going to separate and integrate, let's write this as a single fraction. So let's get a common denominator of 2u. That means I have to multiply the first fraction top and bottom by 2, so I get a 4 there, keep the minus. And then to get a u in this denominator, I have to multiply the numerator by u as well, so I get u squared. All right. Okay, so now let's write this and then see how things separate. right? Because the claim is that this differential equation should now be separable, right? And the looks of it, I think it is. So let's say I take over the dx, right? So I put it in differential form. In fact, let me write this as x du and then 4 minus u squared over 2u times dx. So this is differential form, but it's not separated because I have the x function multiplying du and I have the u function multiplying dx. Those need to be switched. So let's do a whole bunch of multiplying and dividing. So if I multiply by 2u, divide by x, and then divide by 4 minus u squared, this is what happens. Right? Actually, let me think. Wait, going back, just looking at this, I think, actually, because if this is 3 halves, and I'm subtracting 1, so this should be a plus. So this should be a plus, this should be a plus, that should be plus. Okay, so thankfully that doesn't change a lot. But we still have to multiply and divide. So multiplying by 2u, dividing by 4 plus u squared, or I can just write it as u squared plus 4, and then du, and then divide both sides by x, so I get 1 over x dx, right? So you see how careful, I could pretend that that was a mistake made on purpose, but it wasn't. But we really have to be careful with our algebra. There's a bit of algebra that goes into this before you even get to any sort of integration. But now it's in a form where we can integrate. So we have the integral of 2u over u squared plus 4 du, and then this is the integral of 1 over x dx. Right? And these are both relatively easy integrals. This one, is the easiest. We can just write that down as the natural log of x, and I know I'm going to have a plus c here, so that side is done. This side, if you look closely, you can use a substitution method for the integral. Now I can't use u, so I won't use u, but you can use something like t, for instance. So if I let t equals u squared plus 4, then dt is 2u du. And that's what I have right here. So I can use now a substitution to help me do this integral. Right? So substitution helped for the differential equation, and now another substitution is helping for the integral. So we end up with 1 over t dt. So we end up with yet another log. So let's keep going. So this is the natural log of t, and then here we have the natural log of x plus c. So now we have two substitutions to reverse. The first one was for the integral. So wherever there's a t, replace it with u squared plus 4. So we have the natural log of u squared plus 4 is equal to the natural log of x plus c. Now, what we could do right away, we can get rid of the ln's, and this is a very common trick. It's very, very useful, right? We can get rid of the ln's right away by doing this. Do e to the ln of u squared plus 4, and then e to the ln of x plus c, right? So raise both sides, or e to the power of both sides. And then before I simplify the e and the ln, I'm going to write this as e to the ln of x times e to the c. So that's that nice clever trick of factoring an exponential here where you have a sum or a difference in the exponent. So I can write this as this product. But this is just another constant. So I'm going to call this C1, or K if you don't like C1. If you don't like subscripts, you don't have to use them. right? But just recognize that this right here is a constant, and there's no need, there's enough stuff going on here to start carrying constants down that look like this. Just relabel it, right? We have enough to do. So now let's get rid of the e's and the ln. So this simplifies to u squared plus 4. That's not bad. And then over here, it'll be c1 times x, right? Because I have this. I have x times my constant. Now, this is an equation I can work with, right? The way it started, you didn't really think it would be this simple at all, but that's what happened, right? So, but remember, we want y, right? We want the solution that gives us the relationship between y and x. Right now, we just have the solution that gives us the relationship between u and x. But this is where we use the first substitution that we made. See, it seems like eons ago. But remember what we did? We let u equals y over x. So since u equals y over x, yeah, so just put a y over x there, and then we can essentially reverse the substitution. So go back to y now, but again, it has to be that ratio. So y over x squared plus 4 is equal to, and I'll write this as c1x. And it looks like we can actually get this isolated. We can actually get this in an explicit form, which is exciting to me, right? So let's go ahead and subtract 4 from both, and I hope it's exciting for you too. I mean, this is edge of the seat stuff. So properties of exponents there. Let's subtract the 4 from both sides. So then we have c1x minus 4. Multiply both sides by x squared. So we have y squared is equal to c1. Now this would become x cubed, and then minus x squared. Again, doesn't look too bad at all. And then to solve for y, then we'll have to do the plus or minus the square root of this quantity. So we actually get, it almost looks like two sets of general solutions, right? So therefore, y is plus or minus the square root of what we have here. And there we go. Right, so essentially, and the way we would kind of interpret this, there, like I said, there are two sets. So really, it's any function of this form or any function of this form, right, represents a general, or so these represent general solutions of our differential equation. Right? So obviously a lot going on in this. I think this would be something to definitely rewatch. Maybe take it to the point where we started doing the example and try to do it yourself. Do a couple lines, watch the video. Do a couple more lines, watch the video, because you definitely have to get into it and try these, right? It looks straightforward when someone else is doing it, but when you try it, that's when you really know if you're getting it, and if you're processing it and executing all the steps correctly. All right. Well, see you in the next video. So for some more differential equations.